say dou x by dou t, right? So dou psi by dou t minus I omega, right? I want to write this. So what I should do is say multiply by I on both sides. Then it becomes this, right? Then this is minus I into I, which is equal to minus I square, which is equal to 1. Minus 1, then minus plus psi of x by 2 omega. So the omega psi can be written as I psi of dt. Again we have the h, so it will become h bar, right? Okay, so it is nothing but this, right? So E is equal to E psi is equal to h bar I dou psi by dou t. Okay. So let me write down here. E psi is equal to, I'm not writing the xt here, just to avoid save some space. Okay. So as I said earlier, E is equal to kinetic energy plus potential energy. So the kinetic energy is p square by 2m, right? Then p square of psi, let us say p h dash k, and if I take psi, then it's a psi of h bar k, right? And again, if you want to represent the kinetic energy, it should be in the p squared psi, right? Which is equal to, we know this, minus h square just to p square, which we already derived it, minus h bar square second order psi by dx square. Okay, so this is, let us say this is in a one dimension. Let's say we take in a two dimension, three dimension, then what it will become is my h bar square, then dou square by dou x square plus dou square plus dou y square plus dou square plus dou z square of the psi x, y, z. And again, if you talk time, then it will become a four dimension space time. So this is the p square psi. Again, it should have x, y, z, t, right? Now we are trying to do this one, right? So this is E of psi equal to, let me write down in the high level, then I can expand it. Again, before we go there, see what is this? This is nothing but the Laplace operator, right? So p square psi is equal to minus h bar square Laplace operator psi. Okay, so the total energy of the system, the Hamiltonian, is E of psi is equal to what? P square psi by 2m plus the potential energy. Let us say we describe this by V of psi. That's a potential energy. Then if we expand this, then it becomes the Schrodinger's equation. Let me expand that first. E of psi x y z t, right? Maybe I should expand one shot. So we know E of psi is equal to this, right? So this is h bar I d psi z psi xyz t by dt equal to p square by 2m, and we know p square is this, right? Minus h bar square by 2m, and this is the Hamiltonian, sorry, not a Laplace operator, right? Laplace operator of psi x y z t plus v into psi x plus, sorry, x comma y comma z comma t, right? So this is the Schrodinger's equation. This is a time dependent Schrodinger's equation. This is Schrodinger So this is the time dependent Schrodinger's equation. So this equation is used to calculate the probability of a particle in a given space, which is all basically the application of Schrodinger's equation, which I want to take that as the next session. So this basically is the Schrodinger's equation. This again, we derived this by using basic concepts in quantum mechanics and classical mechanics, and the stickler here is this wave function. So this is very it's not very clear even for Schrodinger. People say after he came up with this, what is how this wave function, what can be used, but there are some application, like the basically gives the probability, so dt, so d2 gives the probability of that probability of a particle available in that duration, or not in the duration, in that space. So it basically gives a probability density function. So, but again, as I said, that I will try to describe that application in the next session. So this is basically the Schrodinger's equation, right? H bar I dou psi by dou t is equal to minus h bar square by 2m, the Laplace operator of psi, plus the potential energy, which is V of psi x comma y comma z comma t. Okay, thank you.